Hello there, how you guys doing? Well, it's Sunday, rainy outside, and GreatScott released a new video. And in his video, he talks about LiDARs. And I realized, I've been working with a module that a lot of people, could use, but at the same time, documentation is kind of sketchy. So I realized I'm gonna make a video about this sensor and make the code available for everyone because I believe this LiDAR sensor has some really great advantages compared to the ones that you already know. The market for LiDARs and single point LiDARs have been growing a lot lately, and a lot of new sensors are dropping. So if you're interested in learning to use a kind of cheap and easy to use LiDAR sensor for a project, in my case a drone, well, stick to the end because I believe this video is going to be useful for you. So here in his video, he uses this AliExpress module right here. 20 meters and, 20 meters ideal. I'm going to explain that really quickly, but no, very cheap and good distance, single point. So a lot of people will look at this module and think, oh, I'm gonna buy this one because he made it work in his video, but there are better options out there, especially on AliExpress. Well, I left a comment here, if people were interested in more LiDAR sensors, and I've been working with the XT-S1. So people actually commented and they would like to see that one. So let's delve into it. If you search for LiDAR sensor here, you're gonna have a lot of results. AliExpress sells a lot of stuff. A lot of those are the rotating ones. They get not a grid, but a line of points. Then you have to process that data. And then you have the single point ones. This is the one that GreatScott made a video about. Well, actually, a part of his video. And this module is centered around this sensor right here, DT6012. Well, I never used this guy here. But the important parts for you that is starting to use LiDARs right now is you need the ideal distance. So the maximum distance you can get a measurement with 100% reflectability. And then you usually need if the reflectivity is lower, how far can I sense stuff? So here it says 20 meters ideal distance. But with sunlight on, this is a really high number, by the way, and low reflectivity, you have 12 meters. So you almost half of the distance. Of course, how do these sensors work? Well, they actually just send a pulse of light and then wait for it to come back, divide the time by 2, and then you get the distance. So sunlight can actually interfere with that measurement. Therefore, they use some kind of encoding square wave to kind of, the sensor can differentiate the pulse that is sent from the sun. This kind of information they usually extract from the datasheet and then put on the seller's page, so you kind of can believe this kind of information. So this is the DT6012. How about the sensor I'm talking about? So this is the sensor I'm talking about, and just so you know, the price actually increased. I did not pay this much. Probably they're selling more, I don't know. But this got 30 meters ideal distance. And if I'm not mistaken, 24 with 5% reflectivity. So this is actually a better sensor. The caveat here is this guy is only 50 Hertz. The previous sensor, the one that GreatScott used on his video, is actually 1000 Hertz. So it's better suited for projects that use closer ranges, but you need faster reaction times and measurements. This guy I will use on a slower drone. 50 Hertz is fine. But 24 meters outside, so with poor reflectance and also sunlight. Although you can see here 100K lux, so background light a little bit dimmer than the compared to the other sensor, but so far I've been testing this sensor and sun has not been a problem so far. This guy works with 5 volts and WART or I2C protocols. So let's take a quick look at data sheets and then I'll show you the codes and it working. And by the way, here is the sensor working already. So I'm using an ESP-32S3. I really love using the ESP-IDF, the framework. So I've been using for all my projects so far. And it's just 2 pins for UART, 5 volts and grounds. And here you have this really small sensor, just as the other one. And it is already sensing. I don't know how safe it is to point this. I'm using my poor webcam, so I can use the 4K camera that you're looking right now. And I don't want to damage the sensor, but it's already sensing and it's pointing at my ceiling, which is approximately 1.8 meters away from my desk. So let's check the data sheets and then move on with the code. Every document and image and scheme and diagram, everything you need will be on the GitHub page down below. I'll be probably making a new project just with these codes, but otherwise you can go for my master's dissertation project. This sensor will be using there, so the library is there. But this is the document for the sensor. As you can see, it's nothing new, but it hit the market like last year. It's kind of new to at least AliExpress. And you have some basic information here, you know, voltage and ranges and light information. Here's the accuracy, so it's meant to be used, you know, in longer ranges, close to, you know, far away from the sensor, very close. You should be using other kinds of LiDAR sensors. And you have some noise, and then the wavelength of the laser, which is visible for webcams. And this is the official documentation, but the translation to English is kind of sketchy, hence the fact that I'm making this video. Here's a little bit of geometry, because it makes a cone with, I believe, 2 degrees. Yes, the transmitted angle is 2 degrees and the received one is 1, so it's still very thin beam of light. It is a cone. So the further you get from the sensor, bigger target you need to get a correct measurement. So this is right here. And then you have the different modes. So just to be really quick about how does it work, you can make like, you can trigger a single measurement and read it. Or the way I'm using my sensor is I have continuous active measurement. So it keeps measuring it. I have the filter on, so it filters over time and reduces the noise. Hence the fact that, you know, the measurements are more accurate, because if you just do trigger a single measurement, it's not going to be that accurate. If you keep rolling measurements and then with a moving average filter, it gets better. So this is how I'm using mine, and in the code everything will make sense. Here you have the pins, and I'm using UART. So serial port, easy to use library, especially if expressive, but you can use this sensor with any microcontroller. The code I'll be showing you will be almost, you know, agnostic to the platform, but I'm using expressives. So here comes the tricky part, okay? This sensor uses UART, yes, but uses Modbus over UART. So you have UART, which is simple, but you need an ID byte, then you have the command byte, then the address, and then function and data and everything. So this document doesn't make that easy to understand how you should use. Later on, you have the register maps and the protocols. It shows some examples, and with the examples, I managed to get, you know, this sensor working, but the document is kind of weird. So for you to get proper measurements of the sensor, you will need, no, let's just get some zooming here. You need to transmit via UART the ID, then the command, then address, then you have some data, and then you need to do CRC16. And the documentation has everything, but you kind of needs to, you need to read everything throughout the whole document to understand what they mean by this. But after that, here are the commands, and my code is actually easier to understand, especially when it comes to like register number. This is actually the number of registers. And here is not the address, start address. This is the index. And ask me how you know that. So this document is not the best translation. At least I cannot complain. They translated it. It's better than a document full in Mandarin. But, you know, here I have some registers. And you can read this by yourself. But I'm going to show you the code that makes this work. And, you know, with that code, you'll be able to use the sensor. And if you want to squeeze more juice out of the sensor, then you can read the complete data sheets and then, you know, do it by yourself. But my code makes it work, and makes it work with really accurate results and make it work as fast as you can, 50 Hertz. So let's check the codes, and then, you know, I'll make the demo public on GitHub, and it's everything up to you with to do. But the sensor is actually really great. Let's jump to the code. I'm going to make this file available. I'm going to make an example, just a demo for this, but this whole project is actually my master's dissertation codes. So I have demos here for the servos and the LiDAR and the LED, because, you know, it has an onboard LED that is not tricky, it's not easy to use actually. And I'm going to make a tutorial, you know, how to migrate from Arduino to ESP-IDF using this LED, but that's for a future video. So without further ado, let's just check the XT-S1 sensor from ToFFuture Technologies. And disclaimer, I'm going back to coding after years of only working with hardware, so I'm kinda back to being a beginner in coding, so you pardon my codes. It probably doesn't look as professional as I would like to, but I'm learning, and I actually think it looks not that bad. So this is the library and everything you need to use. You have a setup you have to call before using the sensor. It just configures the registers and use the UART and all that. And then you have a function that writes to register, reads to register. You have just a checkup on the system error. I made a different function just for that. And then you have the function you call to get a measurement. So let's check the functions one by one. So first of all, you have a timeout here for the communication, because you have to, as you use UART, not SPI, you have to send a command to read and then wait a little bit and then check for the input buffer. So this is why I have a timeout here. If in case you disconnect the sensor or something like that, so you throw out an error and then you can work on that. Side notes, for all my projects on ESP-IDF, I changed the tick rate of the system to 1000 Hz. I am using Platform IO on VS Code. So you just go to SDK config, you go to config FreeRTOS Hertz. I changed to 1000. So my tick rate here is 1000 Hertz. The tick period is 1 millisecond. So this timeout here, as I'm using the system tick, is 12 milliseconds roughly. Then I have a tag for my ESP log function. I like to use that to check for errors. And then you have read timeout for the UART. So the internal functions, this is based on UART, so I'm gonna go straight up to setup. As I'm using the ESP-IDF, you need to configure the UART port, makes all the sense, but this is not dependent on ESP. You can use the sensor with ARM STM32, you can use Arduino, you can use whatever. This library should be fairly adaptable to whenever you need, but if you're using Espressif's IDF, should be just plug and play. You have the baud rate, and then 8 bits. The rest is very standard for UART. So I set the pins. In this case is the 4th and 5th GPIO from this ESP32S3. And that's basically it. I'm using UART number 2. Then you have the configurations, and you basically configure the parameters and then install the driver using a buffer for the input but not the output. So every time I'm going to transmit, it just locks the function in place and waits for it to finish. And this is the only configuration you need to make to get this sensor to work. An active measurement, so it keeps measuring, and then you request one to get the latest measurement. And this is, I changed the frequency, the minimum period to 20. You'll basically be writing the sensor to the maximum frequency, which is 50 Hertz. Oh yes, my comments are long. So you go for register index, not address, 66, and then you write 20 in there. Then you go to register 65. I basically turn on the active measurement, so it keeps measuring, and then I turn on the filter, so it keeps measuring and then filtering the results. And then lastly, I go to register index 3, and then I start the active measurement. So I just turn it on basically. I got a ESP log, so I can get the debug message that everything went well. Otherwise, the ESP error check will just stop on its steps. This is for the setup. So internal functions. I have a CRC16 here, and this is present on documentation. The datasheet has an algorithm like that. I just copy and paste and it works. You don't need to delve and try to understand how this checksum works. You can just use it, and that's what I did. I have a flush for the UART port, so good to have. I have a check buffer. This is I use to get especially the timeouts, so I can verify the UART if I got a response for the sensor. And then you go to the 3 low-level, functions, not low-level, but they are very raw. So I have a buffer in here and the CRC. I basically have the ID here, and this is the part of the Modbus, not UART. I have the command, which is dependent on the type of register you're reading. So let me get back to the datasheet. So in this sensor, you have 2 types of registers: holding registers and input registers. Holding registers, you can write to them. Input registers, you can only read. Hence, you need 2 different functions. Why? I don't know. I did not try to use the same reading function because, I'm on kind of a clutch here. I need to make things work fast to finish this project to the end of the year. So I programmed my functions to use functional code 3 and 4 depending on the register number, or better, index. So as you can see right here, you have index 25, it's read-only, and you have index 64, is write and read. This differs the type of register you're trying to read, and then you need different commands. Hence the fact I have that function working quite weird in there. So this is the command I use, and outside this function I do the manual check to see what kind of register it is, and I use the right one, but that's the command 3 or 4. You have addresses, is 2 bytes, is a word, and then you have the count, how many you're gonna read. I usually use only one. I only read one register, 2 bytes. Then you do the CRC, and you have this whole pack of 8 bytes, and then you write to UART. This is how you read a register from the XT-S1. How do you write something to the XT-S1? Same thing. The command now is 6, and then you put the address, value, do the CRC, and write it off. So these are the 2 main functions to use here. Very simple, nothing too crazy. Your ID, your standard ID on Modbus is always 1, and then I have a read buffer is just to read all the bytes that I need from UART. Hopefully the same number of bytes I sent. So those are the internal functions of this library. What you use when using this library for yourself are these functions here. And this one is just a bonus that I used once and never used again. So you need the setup, the measure distance, and that's it. I left the read and write register here just because it's useful for you probably. So what is the write register function, not Modbus, but XT-S1? This guy actually deal with errors and do the checking. So I check if the address, I'm doing it manually. I could do it in a better way, I know. But I do it manually, address index is the registers you can write to. Otherwise, you should block the function. If it's not the right registers, I throw an expressive error invalid argument. So after that, you go inside here, I write a command to the UART, and then I have a function just to check the timeout. If I don't get an answer with 8 bytes back, we probably have a problem, or the sensor is not connected, I don't know. So you have a timeout error that will be returned. Otherwise, if you get 8 bytes back, it's just an echo of your own message. I don't check if the message is correct, because if I have the echo, 100% of the time I got an echo, it was correct, so I just deleted the part where I tested. So I wait for a response, and then I flush my buffer, and then I finish the operation. This is how you write. And to read, it's kind of the same, but now I have a pointer to a value, so buffer with 7 bytes. Then I manually check what kind of register it is, if it's an input or holding one, and then I write with the right command in here. I know this is really crude, there's probably more elegant ways to do so, but this is easily to check and easy to see, so I went with that. If you write the wrong argument here, you throw a wrong argument error. If not, the same. I just written to the buffer, now I wait. If I have a timeout error. If not, I write to the pointer, the 2 bytes of the answer back from the UART. And to finish it off, how do I gotta measure a distance properly without doing all that? Well, in your project, if you use this library, you need only 2 functions. Setup before, using the sensor, and measure distance. Well, this will return to you 16-bit messages. I'm using uint in here, but it actually has signs. More on that later. But I just use the read register here, check the error and return the value. And you understand why. When looking at the demo that I wrote, I'm putting this demo alone in the GitHub, link down below. But, this is just, doing statistics. So I'm going to calculate minimum, maximum, mean, variance, and standard deviation because we need to get accuracy and precision. And I'm going to actually calibrate the sensor and the institute that is helping me to work with this project. But there are some error codes that you can read from the register, and I don't want you to read that datasheet if you don't need to, hence the fact that this is actually -13 to -1, and of course, because, I want to work with that in a proper way, I just add that in an index because this is a pointer. I like to make pointers make sense. But so this is the first error, this is the last error, but I put it in order that it makes sense. So you have SPI errors, you have pixel saturation because of the response of the light response for the sensor. The sensor auto calibrates the intensity of the beam depending on distance. So you have all kinds of different errors here. The sensor also has temperature information inside it. It kind of controls, you know, its temperature. So you have problems with temperature, you throw an error. So this code right here is not that complicated. I just check for any error messages are not included in my statistic calculation here because it wouldn't make any sense, a negative number there. So it just adds to the, you know, maximum, minimum, mean, and then you have variance, prints everything, and it's done. You can check this demo for yourself, but let's just make it, you know, work, and I can show you how this guy goes. So I have my sensor in here, and you can see I throw off some errors in there. You can see the LED for the UART, so I'm throwing some errors because my hand gets too close, the intensity goes up, you throw some errors. But let's just check the serial port. So I adjust the camera here, you can see a little bit of the lab. Actually, we should make a video of the lab because now it's complete, but that's for our next video. You can see here my hands. Ooh, did you see that? Too close. So if you want to measure close, you can actually do that. But after you do a little bit, it stabilizes because it controls the intensity. This is 43 to 45 centimeters. That's in millimeters, the distance in there. So you have the mean, the variance, and then standard deviation, and all that. For close, the error is quite big. For far away, you can see the standard deviation falls really nicely. And that's 1,820 something millimeters from the ceiling. So the sensor is working quite well. Yes, you have to deal with some errors, especially when the distance changed too fast. And I just realized you're not seeing my hands because I'm holding the webcam. I am a silly goose. So there you go. Very dangerous hand position in Germany. So you can change in here. It throws some errors, but it's just, you know, 1 or 2 measurements in 50 that I'm using to average here. So it tracks quite nicely. And of course, you don't need to use 50 measurements and do a statistic with it. You can just, you know, just use 1. So I know this video is not as quick as I intended to, but this sensor has quite these quirks. So I hope you understood, and you know, you have all the resources in the link in the GitHub. I hope if it helps you. If you have any questions or I'm missing some important information, just comment in the video down below. And you know, just a microcontroller and then the sensor, and you almost can see the sensor right there. Oh, there you go. And you know, some errors in the screen, but it's measuring everything quite nicely. So yeah, that is the XT-S1 sensor that you can get right now from AliExpress. And you can download this library I just wrote. Very simple and very crude. I know my coding skills are not as, you know, sharp as they should be, but I'm not a professional dev right now, at least. I hope to get there in the future. There are other sensors on AliExpress that then range for, you know, $100, and they can go 40, 50 meters. And then you can have like hundreds and hundreds of dollars, you know. You can go crazy with LiDAR sensors. But I hope this sensor helps you in your project. I hope you learned something. I hope this sensor can help you in a project. And I hope you were entertained. Otherwise, see you on the next video. Happy hacking. Bye bye.